It's a privilege today to welcome our speaker, Professor Christine Dunn from the University of Durham. She has a PhD in astrophysics from Cambridge, where she worked on theoretical models of the intense high-energy X-ray radiation produced when material falls into black holes before it disappears forever over the event horizon. She then moved to the USA and spent some time at NASA Goddard Space Flight Center. And as part of her work there, she was involved in things from the payload of the Hubble. And we heard about the Hubble, those of you who were here for seminars last term. She returned to the UK, first to Leicester and then to Durham University, and was proud to be the first woman professor of physics in that university. I think that's correct. She says she's interested in anything that has a decent gravitational field, and she specializes in combining theoretical and observational model data on what happens to a material when it falls into a black hole. So will you join me in welcoming Professor Christine Dunn, who's going to talk on gravity, black holes, and ultimate reality. Christine.
Thank you. So yes, I'm a rocket scientist. I work on black holes. My childhood hero was Spock. So in many ways, one of the reasons I am a scientist is I wanted to be Spock. Drawing a veil over my childhood, let's move on. Black holes in science fiction, like I said, one of my incentives to be a scientist was just looking at some of the science fiction movies. They take these amazing ideas about black holes and they use them as, they use them as plot devices to do wormholes in space, to do time travel, maybe as portals to alternate universes. And so this is what got me into studying black holes. But it's also quite interesting in other ways, in terms of the really big questions. Is this universe all there is of ultimate reality? Is this universe all there is? Now, this gets you into sort of metaphysics in terms of multiple universe, but it also gets you into the kind of bigger questions of life and the questions about significance and meaning and whether or not there's a God. So we're going to go for all of those because, hey, why not? And but first, let's do a quick run through for black holes. And if we're going to talk about black holes, we need to talk about gravity. And gravity starts, in many ways, with Newton. And Newton's theory of gravity was amazing. It's an amazing leap of insight. The urban myth goes that he was sitting under a tree trying to understand something about how the moon went around the Earth. And the story goes that an apple fell from the tree to the ground beside him. And that he looked at this and thought, oh, maybe that is the same as the reason the moon keeps orbiting the Earth. This is an amazing leap of imagination. We think of it as obvious now, but it's actually an amazing synthesis of two very different things. It's an amazing leap of imaginative connection between the two. And so he worked it out mathematically, and his equations they're amazing. You can use them, we teach them to undergraduates, they can do computer simulations of what they would need to fire rockets to the moon. Newton's equations, basically all you need for that. But on the bigger question, Newton was entirely silent. But surely the bigger question is, what is gravity? And actually Newton was asked this. They said, yeah, this mathematics is great, but what is gravity? And Newton famously replied, I frame no hypothesis, meaning haven't a clue. He'd done enough. Come on, it was an amazing imaginative leap. So, and that's where things stood. for hundreds of years. We had Newton's equations that described how gravity behaved, but on that bigger question, the more physical question, if you like, what is gravity, he was completely silent. Until Einstein came along. And Einstein's general theory of relativity isn't just a better way of calculating the effects of gravity, though it is, without Einstein's corrections to Newton's equation, your GPS would not work or would not be so accurate. But more fundamentally, Einstein gave an answer to that more basic question: what is gravity? And Einstein said, think of it like this. Think of space-time as like the surface of a trampoline. For some public lectures, I do actually have a trampoline, but it wouldn't have come down very well on the train. So I have a trampoline, and I get audience participation and stand them on the trampoline, and you can see the surface of the trampoline curve when you put a person on it, when you put mass on the surface of the trampoline. And so Einstein goes, think of gravity as like this. We have the surface of the trampoline, and if you haven't got any mass on that, on the surface of space-time, and then you just roll a test mass along it, then it will go in a straight line at a constant speed, just like Newton's equations. But if I then put mass on that surface, it curves the surface, and then anything that has to go over this curved surface of space-time, its path is curved, not because of any strange force, but just because it's walking on a surface that's curved. And so the easy way to describe this is to take some very, very obedient ants and put ink on their paws, claws, not quite sure, on the appendages. And they're very obedient ants, so you set them off together and say, go north, go due north. And if the ants go due north on a flat surface, like me walking on the surface of the floor here, left foot, right foot, middle foot, left foot, right foot, middle foot, left foot, right foot, middle foot, equal-sized steps on equal sides. On a flat surface, you go in a straight line at a constant speed. And so my two ants, they're going in parallel lines. Distance between them doesn't change. Now let's do it on a curved surface. Suppose I set my two ants off at the equator of a sphere. And I say, head north, head due north, left foot, right foot, middle foot, left foot, right foot, middle foot. The ant on the left looks over its right shoulder thinking, I'm sure they're getting closer. And the ant on the right's going, yeah, they're definitely getting closer to me as we're both heading due north, but we're doing natural walking. We're doing equal-sized steps. We're walking in a natural way. We should be parallel. There must be some inexorable force drawing us closer together. You could think that, yes. Or you could just say you're walking in a natural way, but on a surface that's curved. And so this is the big idea. This is Einstein's what is gravity? Gravity, think of it like the surface of a trampoline, and that surface is bent whenever you put mass on it, and then any other mass coming around, anything else that's traveling over the surface of space-time, that curvature of space-time determines its path, tells it how to move. Summed up in this little sentence, matter tells space how to curve, curvature tells matter how to move. Okay, so then we have just a very different picture of gravity from sort of Newton's gravity, the sort of stuff we teach at GCSE where gravity is a force. It's a spooky action at a distance force. Look, the moon's there, the Earth's here. Oh, look, no hands. Yeah, physicists, we don't like that. Instead, this transforms it to a local response to the curvature under your feet. The Earth is here, it has bent space-time, and that curvature of space-time extends out to under where the moon is, and the moon's walking in a natural straight line path, left foot, right foot, middle foot, but on a surface that's curved. So its path is curved. Job done. Of course, when I plot it like this, we all do this, but some of you are sitting there thinking, yeah, but it's not flat like that. It's in 3 dimensions. Well, actually, it's in 4 dimensions because there's time as well, but it's just too difficult to draw. I managed to find one picture on the web that tried to do this kind of 3-dimensional curvature warping of space. But then you're in trouble anyway because you haven't got time in, and time and space are the same thing in Einstein's general relativity. So Einstein's general relativity gives you something absolutely for free. It gives you for free that gravity affects light. Because light travels over the surface of space-time. Surface of space-time is curved, means the path of the light will be curved as well. Whereas in Newton's gravity, gravity affects things with mass. And already at the start of the 20th century, they knew photons were massless. So it was a kind of a, should gravity affect light or not? Whereas Einstein's completely clear. Gravity will affect light because light has to travel over the surface of space-time. And so its path will be curved if the surface of space-time is curved. And so this was one of the first tests of general relativity. The idea that in our solar system, the sun has got the biggest mass, so it's got the biggest space-time curvature. If we manage to get a star, one of the distant stars that just happens to be along the line of sight between, with the sun in the middle and us, one side of the sun and the star a very long way away, but the other side of the sun, then its path is going to come very close to grazing the limb of the sun. It goes through these regions of space-time curvature, and so its path gets curved. We think light goes in straight lines, and so we see the position of that star being shifted. And this was one of the first tests of general relativity, and it worked. It worked quantitatively. Einstein's prediction got it exactly right. So this is then how to think about gravity. And it's clear then that gravity affects light. So what can we do with that? Well, let's think about how we could play with the strength of gravity. This is a cross-section, highly stylized, through our solar system. The sun is that yellow blob, and the white kind of grid points show you how it's curving the surface of your space-time trampoline, and the green dot is the Earth on its red orbit going around the sun. So here we are with a green dot going around. The Earth is traveling in a natural straight line path, but it's on a surface that's curved, so its path is curved. And what would happen if we made gravity stronger? Well, there's 2 ways of making gravity stronger. You can put more mass in the same space, or you can take the mass you've got and you can put it in a smaller space. You can squeeze it down. Since I don't have any way of getting more mass onto the sun, I'm going to think about what happens as I squeeze the sun down. Okay, so that's what happens. Oh, but look, that's really interesting. So I've squeezed the sun down, so I now have access to these regions of highly curved space-time that I couldn't get to before because it was inside the sun. But the curvature around where the Earth is still the same. I can now get to regions of stronger gravity, but the Earth's orbit hasn't changed. So let's squeeze it again, make gravity stronger again. Okay, and same thing again. I've got to regions that are much stronger gravity, much higher curvature, but where I am with the Earth hasn't changed. And this is where we're sneaking up on black holes. We're making gravity stronger and stronger and stronger from the surface of the sun's mass, because we've squashed it into a smaller region. We've got access to these more highly curved regions. Gravity is stronger. And if gravity is stronger, then the escape velocity, the velocity at which I'd have to be going in order to get all the way out from the gravitational field of that will be going up and up and up. And actually, let me throw something up. So you can think of escape velocity quite easily. If I throw this kind of slowly, doesn't go very far. If I throw it faster, goes further before it comes down again. If I throw it really fast, I could get it out of the Earth's gravitational field. The stronger I make gravity, the faster I have to throw it. Eventually, if you make gravity strong enough, you have to throw it at the speed of light. That's unfortunate because you can't go faster than the speed of light, and so if you then made gravity stronger still, not even light could get out. That's what defines the event horizon of a black hole. Oh, but look, the curvature around the Earth's orbit is still the same. So even if the sun were to become a black hole, which it won't, it's not massive enough, even if the sun were to become a black hole, actually nothing would change at the Earth's orbit. The Earth wouldn't get inexorably sucked in. The curvature it sees under its feet is the curvature that it sees now. So apart from the fact that all the light from the sun would not get out, and so all the plants would die, so all the animals would die, so we would die, apart from such minor considerations, everything stays the same. Good. Now we've cleared up that misconception about science fiction movies. Actually, I find an easier way to think about it, actually, is to go with space-time itself falling into a black hole. If I'm swimming in a river, suppose there's a river coming towards me, and I'm swimming against the current. If my swim speed is faster than the speed of the current, I will make progress forward. And so the way to think about this event horizon is that space-time itself is kind of falling in towards the black hole, and at the event horizon, the speed reaches the speed of light. So it's like the light beam is swimming, trying to get out, so it's swimming against the current, but at the event horizon, its maximum swim speed is not as fast as the speed of the current sweeping it back. So even though light is trying to go radially outwards, space-time itself is sweeping it back into the black hole. And that is actually mathematically, it does work. And it's a nice way to think about what's going on. So that sets the picture. That's how we get black holes. That's what I do for a living. I think about black holes, but they are utterly extreme. If I was to take the Earth and make it into a black hole, I need to squeeze it. That's too big, actually. It needs to go to something between my thumb and forefinger. Less than 1 centimetre, the entire Earth. That's how small I would have to squeeze it in order to make gravity strong enough to make space-time curve back on itself to make me an event horizon. By which time you're going, that's not going to happen. Why are we even talking about these things? Well, it's not going to happen for the Earth, but if you take a really massive star, more massive than the sun, then at the end of its life, you get there. Because all stars shine by fusing hydrogen to helium. And if you put these on a balance, start off with 4 hydrogens, you end up with 1 helium through a quite interesting multi-component collision process. But ultimately, what you start out with on that side is 4 hydrogens. What you end up with is 1 helium, put them on a balance, and your 4 hydrogens are somewhat heavier than the 1 helium you end up with. Einstein, in that most famous equation ever, E equals mc squared, energy and mass are the same thing. And so if you lost some mass, you gained some energy. That's what makes the sun and most the stars you see in the night sky shine. Also, we're just making the chemical elements. We've transmuted the chemical elements, gone from hydrogen to helium. This is where you make the whole of chemistry, which of course makes the whole of biology. So I'm afraid all the sciences are just a subset of astronomy. So it's that energy from fusion that keeps the gas inside the sun hot, that keeps it expanding out against gravity pulling in. The sun and all stars are finite. At some point, they run out of hydrogen to keep the gas hot, to push out against gravity pulling in. Gravity doesn't go away or run out. And there are various kind of last-ditch screams that the star can do. It makes use more of the chemical elements, but eventually it all goes hideously wrong. And by the time you get through part of the periodic table, the star implodes. If it's massive enough, the compression on the central core, we know of nothing that can hold it up against ultimate collapse into a black hole. And this collapse is marked by dramatic supernova explosions, where a single exploding star can outshine an entire galaxy of 100,000 million stars. So here is a dying star. For a couple of months, that star, one dying star, is brighter than 100,000 million other stars in another galaxy, which are fusing hydrogen to helium. This is an incredible explosion. And at the end of it, for the most massive stars, we know of nothing else it can be other than a black hole. That sounded plausible. But how do you test that? Because the thing about a black hole, its main distinguishing feature is it's black. And the thing about space, your basic space color is it's black. How are you meant to see them? Looking for a black hole on the black background of space, not a good idea. Not what I do. I do stuff that's easier. Because most stars actually, our sun is a bit unusual. It doesn't have any friends. Most stars are in binary systems. And so when one star evolves to the point collapses into a black hole, its companion star can be lunch. And so material can spiral down into this enormous gravitational potential. Whenever material falls under gravity, you get energy. That's how hydroelectric plants work. And so that energy heats up this infalling material and heats it. There's a lot of gravity, so it heats it not just red hot, not even white hot, but glowing X-ray hot. So what you need to do is you need to look at the sky with X-ray eyes to see these glowing disks that are highlighting the position of a black hole. Problem is, X-rays do not get through our atmosphere. So in terms of the total spectrum of light, you're going from radio waves all the way up to X-rays, our atmosphere's opaque for a lot of the time. It's like looking through a brick wall. In X-rays, it's really like looking through a brick wall. In the UV invisible, obviously we can see. And then bits of the radio we can see, but the rest is completely blank. If you want to look at the sky with X-ray eyes, you will see nothing if you're on the Earth's surface. The only way to go is to play with rockets. So I'm a rocket scientist. And so this is actually how black holes, real astrophysical black holes, were discovered, how we have evidence that such exotic objects actually exist. So way back in the 60s, when the space race was just starting and satellites were just flying above the atmosphere, they just stuck an X-ray detector on a rocket and thought, I wonder what we'll see here. And what they saw was something completely unexpected. They had not thought, oh, well, maybe we'll see these glowing X-ray hot disks of matter falling into a black hole. No, they hadn't thought of that at all. It was like, oh, my goodness, what's that? That's bright. And so X-ray astronomy, putting an X-ray detector on a rocket, this transforms black holes from some theoretical, speculative extrapolation of Einstein's gravity to something observable, to something we can actually look at, observe, and try and understand. But the corollary is, if you do black holes, you get to play with rockets and be a rocket scientist, which, I mean, introducing yourself at parties, hi, I'm a rocket scientist, I do black holes. It's great. My husband is a mathematician. Not so great. So now when we look at the sky with X-ray eyes, this is what we see. So this is an image of the whole sky. Every dot is a source of X-rays from some sort of system. The red ones, you see, they're all on kind of the line in the middle of this plot. That's because this is done in coordinates centered on the center of our galaxy. And so those red dots, they're tracing out sources in our galaxy, intense X-ray sources in our own galaxy. And many of these are systems like we just talked about, where you have a black hole with an X-ray hot disk of gas, of material falling onto it. It's kind of like the final scream of this material before it's swept below the event horizon, lost to the universe forever. But you can also see these blue dots that are kind of more uniformly scattered over the sky. And those, many of those again, are black holes accreting from an X-ray hot disk. But now we're not talking about black holes formed from the collapse of big stars. We're talking about supermassive black holes, maybe 1 billion or 1 million times the mass of our sun, that can form in the very centers of galaxies from very dense systems of gas and dust and stars there. But again, you have a disk of material falling onto the black hole, gets heated up, and you get this hot X-ray emission. So this is actually what I do for a living. I study what happens to this material. How exactly? I've made it sound so easy. Oh, you heat it up, it produces X-rays. Could we have a little more detail in between those two halves of the sentence, please? How exactly does that work? So that's what I do for a day job. And if we can understand how this works, then what we've got is a bright source of X-ray emission really close to a black hole, really close into these regions of strong space-time curvature. So can we use them to test Einstein's gravity in the strong field limit? So that's the day job. I have the best job in the world. So if we have these things, if we have black holes, I can point you out some, then what about all those science fiction? Can we use them for time travel? Could we go back to the past and build a time machine, travel back in time, meet my grandfather? If I'm of an evil disposition, I could kill them. Only then my grandfather's dead, and if that was before he gave birth to my parents, then I'm not born, which means that I didn't build a time machine or go back in time to kill him, which means he is still alive, which means I am born, yeah, that doesn't work, for which I think we're all deeply grateful. Back to the Future being the one that popularized that. But yeah, the future. Yes, you can use black holes for time travel to the future. That's easy. That's science fact. Time travel you can do, but only one way. You can do time travel to the future. Gravity slows down time, so you can travel into the far future. And this was a plot device in the movie Interstellar. And actually, yes, it works. You can do that. Time travel is very easy. In fact, I bought a time machine with me. You think I'm joking? I'm not joking. I'm a physicist. Let's do this. Okay, we're going to do time travel. Here we go. 1, 2, I'll set it going. 3. I just traveled through time. I traveled to the future, but so did you. So you didn't think it was that impressive, but actually it is quite impressive. We're all moving at the speed of light through space-time. And most of the time we just take all of that speed and we put it through time, and we get older, no matter how much we try to deny it. But if instead we took some of that fixed speed through space-time and put it through space, we'd grow older, we'd have less motion through time. So we'd grow older less fast. So our human lifespan could take us to thousands of years into the future. And it's similar with gravity as well. If you're in a strong gravitational field, you slow time down. You can travel to the far future. So would you want to? Everyone you would then know or care about would be dead. Take them with you. So what about the using them as wormholes to an alternate universe then? This is the sort of thing you get as the storyline in various sci-fi. You fall into a black hole and it's a portal to another universe. Interesting. Probably not, but at this stage we have to say that actually we're not that good at physics. We can't do physics at this level. So what's at the bottom of a black hole? We talked about the event horizon. That was all really easy physics. We can do physics up to that point. But Einstein's equations, when you take them all the way down to the bottom, they start saying that at the bottom of a black hole is a singularity, an infinitesimal point of infinite density. Now, when you get infinities out of your equations in physics, it means you've done it wrong. It means you've taken them somewhere they didn't want to go and they've broken. And gravity, Einstein's gravity, is the best theory we have for strong gravity. It's the only theory we have, basically. But strong gravity on fairly large-ish size scales. When you get small size scales, we have quantum mechanics. Quantum mechanics is the way to deal with things on small size scales. But quantum mechanics and gravity don't talk to each other very well. So if you have very strong gravity on very small size scales, we don't have a theory for that. We know we can't use Einstein's theory, and we know we can't use quantum mechanics. So where we're dealing with very strong gravity on very small size scales, we can't do it. We can't calculate that. So actually, what's at the bottom of a black hole? Could you use it as a portal to another universe? We don't know. What about other universes anyway? Are there other universes? What about the Big Bang? That's where our universe came into being. What about other universes? Could it have spawned other universes as well? Is our universe part of a multitude of universes? Let's call it a multiverse. So if we could understand what happened at the Big Bang, we'd need to be able to calculate really strong gravity on really small size scales. Oh, you mean where we don't have a good theory? So maybe our universe is part of a multitude of universes. Maybe black holes are portals to other universes. We don't actually know because we can't do that yet. I hope one day, in my lifetime maybe, I'd get to see a theory of gravity that quantized, that would let us calculate these things. But until then, we haven't got it, so we can just speculate. And speculating about a multiverse, a multitude of universes, has kind of some intellectual respectability because we live in a very, very strange universe. It's hard to describe just how strange our universe is in terms of its fine-tuning. It's a really odd place. It's been described as, it's almost as if the universe knew we were coming. It's very hard to actually make a universe that has the right sort of physical laws to produce life. Where do we get the physical constants from? Why are they the way they are? And why are they the ones that happen to allow the complex chemistry that is clearly required for any sort of life? One very small example, we talked about nuclear fusion in the center of stars. The way we used nuclear fusion and built up the chemical elements, made of chemical elements. You need to do complex chemistry, so you need elements more complicated than helium and hydrogen. But actually, if the strong force was slightly different, that wouldn't happen in stars. You wouldn't get complex chemistry because you wouldn't get the chemical elements if you just change the strong force constant by a bit. And we don't know what sets the strong force constant. Why? Why are the fundamental constants set at values which allow the emergence of life in our universe? And so this is why the multiverse has become very popular, because if you have a multitude of universes and you don't know what sets the constants, but they have some set of physical constants, maybe each universe has its own set of physical constants, then maybe if you do an infinite number of universes, then one of them has physical constants like our universe where you can have life evolving. And of course, we're in that universe and it looks special to us, and it is special, but it's only one of an infinite number. And so statistically, it's not that surprising. It's amazing the lengths people will go to avoid God. But in some sense, I was never that impressed by arguments like that when I was an atheist. I used to be an atheist. I did not grow up with any sort of faith background. So, yes, fine-tuning of the universe, maybe it points you to a God, but maybe it just points you to a multiverse, a multitude of universes, each with their own set of physical constants. Or even looking more generally at the Big Bang. It's a very surprising event, isn't it? You might have thought. And fundamentally, it's the question about why is there something rather than nothing? Well, maybe you can answer that with quantum fluctuations. Similarly, okay, look at the complexity of life. Arguments from design have always had some traction. Why is there something rather than nothing? Why is there such complexity? Well, you can answer that by evolution. We might not know much about how life starts, but hey. So often I've seen science, people trying to make this sort of intellectual, very general philosophical argument about faith from looking at science. But I never found that particularly convincing, because there's always a possibility that you could do this without. But I think one thing that you do get from looking at this universe, you do get that if there is a God, they are far beyond us. Any God that could create this universe or multitude of universes is so far beyond us as to be incomprehensible. I mean, if there was an ant on the floor, which of course there isn't because this is a college and kept to amazing standards of cleanliness, but if there was an ant on the floor, I would have, I share some DNA with an ant. I have more chance of having an understandable conversation with an ant than I would have a grip on any God who could create a multiverse. They are so far beyond my limited humanity. And in the same way that a creator would be separate from their creation, space, time, matter, energy, these are part of our universe. These are part of the created world. So science tools study space and time and matter and energy. So science then probably won't help us very much. These are tools designed for stuff in the created world. And a God outside of his creation, okay, that's not space, time, matter, energy. We're in. So how could we even know that God? How could we, as limited humans, ever get our head around a God like that? Well, I don't think we can. I think it would need God to reveal himself to us. And so this is where my journey of faith started, that all faiths have at their core this idea of revelation. We need God to reveal himself to us. And there are prophets, there are teachers showing us the way to God. But Christianity is unique in that it's saying God himself came to us in Jesus. that he's a human sharing our humanity. How could you do that with God? But whose essential identity was God. And so yes, for me, I was an atheist because I wanted to be a scientist, and I thought scientists had to be atheists because I grew up in the 70s and we weren't very sophisticated. It wasn't until I tangled with some of these ideas about evidence for faith, evidence for Christianity, when I was 17. Went to my friend's church, saw people worshipping like they meant it, and I came up with the kind of classic arguments, oh, how could there be a God? And they asked the classic question, who do you say Jesus was then? And I go, good teacher. Really bad answer. Yes, he had some good teaching, but he let people worship him, and that's deeply disturbing. He was either mad, thought he was God but he wasn't, that counts as a nutter in my book, or he was manipulating people. He knew he was God, but he was letting people worship him anyway. Ooh. Or he was God, in which case worship is the right response. So let's think about this as a scientist, okay? Which one of those three would you like? So I decided I didn't want any of those because, and besides, Jesus didn't necessarily say he was God. It was his friends who caused the Bible to be written, caused the New Testament to be written. They said he was God. Now, my friends are quite unlikely to mistake me for God, and the more they know me, the less likely they are to mistake me for God, but we'll gloss over that. The worst thing was the sort of thing they then said about their friend, which was not only did people worship him as God, but that he was horribly killed, they ran away, I could understand that, and then Jesus was raised to life again, and they had breakfast with him. Excuse me? Really? Really? And what rattled me more was that there was evidence for this. Psychological evidence, okay, but it's still evidence. We know what human beings are like to some extent because we are one, much as I would like to be Spock. The psychological change, the disciples changed from running away in fear to boldly saying Jesus was alive. I could imagine them running away in fear. I could imagine them being so racked with guilt that they would stand up and say, this Jesus you crucified was a prophet, a good teacher showing us the way to God. I could imagine them doing that out of guilt. Could not imagine them saying, this Jesus you crucified got up from being dead and we had breakfast with him. But there's also physical evidence because where was the body? The Romans didn't want trouble. They didn't want another group of religious nutters in Jerusalem. They wanted the problem gone. If the body had been in the tomb, they were Roman, they weren't that subtle. This Jesus you say is alive looked pretty dead to me. So, we're scientists, we weigh evidence. We've got evidence. What's the explanation? Body not in the tomb. Maybe the disciples stole it, but then they'd know it was a lie. And they're not really likely to die for something they know is a lie. Let's try again. Body's not in the tomb, someone else stole it. But then why do the disciples say it's alive? Yeah, let's have a mass hallucination. That means two very unusual things happen. In my job, I'm not allowed to have the tooth fairy twice. I'm allowed one unusual occurrence in any paper, in any research paper. You're allowed one, not two. So then what else? Well, we could always try their explanation, which was the body wasn't in the tomb because Jesus was raised to life, which would indeed convince them that Jesus was God and that life and death were kind of fine, really, because they knew someone who'd been there and worn the T-shirt, so they're fearless, and this does explain the observations. And so this is kind of my story. It's evidence it's not proof. But actually very little in science is about proof, as in axiomatic mathematical proof from axioms. Most of it's like Einstein's gravity. Einstein's gravity, you can't prove it. You can't prove it. You can't prove that gravity works that way. It's just the simplest way of writing mathematically that gravity is caused by space-time curvature. Works extremely well, but it needs that leap of imagination and intuition. It's not proof from axioms. Yes, mathematically he worked it out, but that first bit is not provable axiomatically. But yes, I didn't really want Christianity to be true because I would then be wrong. That's bad. But eventually I decided I had seen enough evidence that I was intellectually convinced. So I'd better do something about it. And then this surprised me as well, because I'd thought of religion, I'd thought of it as a set of intellectual beliefs. But all the books I'd been reading about evidence talked about it as a two-way street, about a relationship. And so I'd just like to end by telling you a little bit about this relationship, which surprised me a lot. You see, I can be a little bit different. Now, I know that startled you. I know you find that difficult to believe, but I'm a woman, which it makes me a bit unusual among my colleagues. So it's been unexpected that I'm a scientist. Many people find that a little strange. But I'm a scientist, so sometimes people find it unexpected that I'm a Christian. And I'm a Christian, so sometimes people find it unexpected that I'm a feminist. And sometimes I just feel that I'm just a bit odd. I do not want your comment. And in the middle of one of these kind of times, I was talking to God about it. And it's not an audible voice, but a kind of voice in my head. If you're into psychology, you could say it's just part of your thought processes. But often this voice in my head makes more sense than all of my thought processes put together. Chris, do you understand gravity? No. If you thought about gravity every day for the rest of your life, would you understand it? No. I do think about gravity every day because I am a black hole physicist. Would that change the fact that your feet stick to the floor? No. This is a very bizarre conversation to be having in your head. Do you understand my love? No, but I'm not thick and I can see where this is going and I think I'm beginning to cry. If you thought about my love every day for the rest of your life, would you understand it? Would that change the fact that I love you? That actually changed something in me. This relationship, it changes us, transforms the way we are and what we do. Thank you.
Thank you, Christine, for that, for the science and for your own journey in that as well. We've got 10 minutes or so for some questions, and I'll have a brief pause and I'll look around to see any hands going up. There's a lady in the middle there, and wait for Rachel to come with you with the microphone.
Sorry, I probably got this wrong, but going back to the science, when you were using your swim speed analogy, it sort of seemed to me that you were sort of suggesting that the speed of the river against you was actually exceeding light.
Mm-hmm. Yeah,
How
that's
does that?
Okay. Right, so this is a fun one. Think about it for the Big Bang as well, because that's maybe something easier to think about. Oh. So you've got the Big Bang expansion of the universe, and it's an accelerating expansion. And so pretty soon there are parts of the universe that are speeding away from each other at more than the speed of light. And that's your observable horizon. But that's okay. The thing that's not okay is to have things, causality, that goes faster than the speed of light. space-time itself can easily go faster than the speed of light. I love physics. Makes my head hurt.
So you've lost me there. It's just space-time itself can go faster than the speed of light. But
If you think about the expansion of the universe, it's very easy to go faster than the speed of light. Very easy to have the parts of it expanding away from each other, but they have no connection with each other, so it's okay. You're not...
I'm not a physicist. I think we'll take another question.
Something easier.
I can just shout, what was there before the Big Bang?
Good question. What was there before the Big Bang? We'd love to know the answer to that question. To do that, we'd have to follow the physics through the Big Bang, which we can't do because our equations break there, because we're talking about all the mass energy of the universe in an incredibly small piece of space. And so the curvature, the strength of gravity on those small scales, our equations break there. So we can't tell you what was there. However, one answer might be, if in this Big Bang, it's not just matter and energy exploding into pre-existing space and time. In Einstein's equations, it's space and time and matter and energy expanding together. That means that before the Big Bang, there was no time or space. And if you manage to be able to visualize that, you're doing better than me. More questions?
Here's one just here. Wait for the microphone to come down with Rachel. Thank you.
Yes, you talked about one of the philosophical questions, why is there something rather than nothing? And I'm actually personally not happy with the, if you like, the excuse that there were quantum fluctuations, because that's not nothing. But I'm more interested, I think, in the fact that we are conscious beings and we have self-awareness. And it seems to me that has to be also a characteristic of whatever it was responsible for creating the universe. And that's one of the reasons why I believe in a personal God.
So I think we look at things like conscious self-awareness. We look at things like the Big Bang. Why is there something? We look at some of these big questions. And when I was an atheist, I did look at them and think, okay, I don't have a good answer, but I will believe that actually if we knew more physics, maybe we could find answers. And so, so I didn't find those didn't find them ultimately persuasive, although they are pointers, I think, to make us look for more. One of the things that I find concerns me a bit is that if we look at things like consciousness, which are clearly very difficult to understand, then if we point at them and say, well, this clearly shows us something about God, this shows us that there's a God, then don't know if there's any neuroscientists in the audience, if we get to the stage where we start to understand consciousness, and I hope we do one day, then it kind of makes the space for God look smaller. Whereas I think if we could understand something about the physical basis of consciousness and how it emerges, then actually that would be such an amazing story that it would make God look bigger. So I think it's a pointer. I think some of these things are really pointers, or signs, but signs you only see if you're looking in the right direction. As an atheist, I was quite happy just to go, yeah, physics, it's complicated. Yeah.
There's a question here, and then one at the back there, and then we'll review how we're doing for time.
Is space-time just a metaphor? In reality, is it just as spooky as Newtonian action at a distance?
Very good question. Is space-time just a metaphor that we've put? We don't know what space-time is. On some level, you could say, is space-time actually continuous, or is it kind of granular? What's the structure of space-time? If we knew that, we'd be doing a lot better. This is physics, we don't know, but I hope one day we will.
Thank you. And there was a hand in the middle of the back there.
Thank you for your talk. The metaphysical always requires a leap of faith, rationally speaking. I'm wondering, in deciding Christianity was the truth, did you compare it to other belief systems, or was it just what you were familiar with and therefore thought that that was the most appropriate leap of faith for you to make?
So, another very good question. So, in many ways, I discovered faith actually by looking at Jesus. So at that point it has to be Christianity rather than any other religions. But in terms of looking at other religions, looking at their picture of God, in many ways what you see, there are some common threads that come through a lot of them. But in Christianity there is something very unique about Jesus Christ. And it was that, it was the evidence for God actually coming to be one of us that convinced me and was for me the thing on my journey of faith.
Thank you. I think we'll draw things to a close there. Thank you, Christine, for taking us through some remarkable science and for sharing your own journey with us. You talked about stretching of space and time, and I think we can all say that our minds in one way or other have shared in that stretching event. But can you join me in thanking Christine for today?